All right. Let's be really clear on this Newton's laws of momentum. It says state the condition of the momentum of the system to be conserved. So let's be really clear. For the momentum of a system to be conserved, there can be no external or outside. External, I'm going to give it all consonants. External, outside, or net force acting on the particles in the system. That would be a really good way to say it. Okay. Everything else, the IB is absolutely not going to count. All right. Now, for this next one, frozen pond is the classic frictionless scenario. And we're throwing a ball, air resistance and friction are negligible. So how does Newton's third law of conservation of momentum apply to the ball as thrown? This is what we're going to write. The initial momentum of the system is 0. The ball is thrown in one direction and has a small mass and acquires a large speed. Since momentum is conserved, the final momentum also needs to be 0. Therefore, the person moves in the opposite direction of the ball. Since their mass is much greater than the ball, they move at a much slower speed. And just to be clear, this is the whole explanation. And there's one last thing. So, and I'm going to add, you know what, I'm going to shrink this and add one more little line to this because this is important. Requires a large speed. Let me just clean this up. So. Since momentum is conserved. Okay, so the initial momentum of the system is 0, the ball is thrown in one direction, has a small mass. Okay. And let's be clear. Another way to say this is that the ball applies an equal and opposite force on the person who is throwing the ball. That's Newton's third law. So you notice I explicitly mentioned the third law and the conservation of momentum. So there's just no way to get a partial credit on these unless you know exactly how to answer the question precisely. And I'll tell you my clues. The person on the pond throwing the ball question is the classic conceptual physics conservation of momentum question where you have this situation and then it moves like this. Right? Now, people did a little bit better on this one. Explain with reference to Newton's second law why the horizontal momentum of the ball remains constant while the ball is in flight. So we'll just talk about that. So horizontally, there are no forces acting. Therefore, the velocity of the ball in the horizontal direction remains unchanged. There is a downward force, but this does not affect horizontal momentum, horizontal velocity. Therefore, the ball maintains a constant horizontal momentum until it hits the ground. And that's the idea. All right, now here, just a small thing, just so you know. So we have a power and we have a speed, and we want to get the force. So it turns out we've got two definitions of power. One is power is work over time. Another definition is power is force times speed. And apparently in this case, the force that we're talking about is the friction force. So we have 0.75 megawatts, so that's 0.75 times 10 to the 6th equals F times this 44. And I can go ahead and isolate F, and when I do that, I'm going to get 17,000 newtons. All right, so on this page, here we go. A locomotive engine gives a truck X a sharp push, collides with a stationary truck Y, and let's just figure this out. So this is going to be conservation of momentum. So whenever you have a collision, we're going to conserve momentum. So I'll have mass of the truck, V of the truck, plus the Y truck is not moving, and then they hit and move with a common final speed. So I have 3.7 times 10 cubed times its speed, which is 4, equals 3.7 times 10 cubed plus 6.3 times 10 cubed, both times V. So I'm going to end up getting here 3.7 times 10 cubed times 4 equals 10 times 10 cubed times V. And so when we go ahead and solve for V, we're going to get about 1.5 meters per second. Now, next it says determine the kinetic energy lost in the collision. So we need 1/2 mvx squared. This is before. And let's go ahead and combine their masses. We're going to say 1/2 times mx plus my times their v final squared. And we're going to compare those two. So I have 1/2, 3.7 times 10 cubed, times 4 squared, which is 16, and that's going to be 1/2 times 10 cubed times 1.5 squared. So when I subtract these two, the amount of energy lost is going to be 18,000 joules. The trucks come to rest after traveling a distance of 40 meters along the horizontal track, and we want to determine the average frictional force. So this is actually a problem that I did as an example for you in class, where we said work is force times distance, and we're going to use the frictional force as the force that's doing the work. So the effect of this is the change in kinetic energy. So we're going to say the friction force times this distance of 40 meters equals 1/2 times 10 times 10 cubed times 1.5 squared. That's final speed is 0 minus this, so final kinetic energy 0. So when we actually isolate the force of friction, we're going to end up getting about 280 meters of distance. All right, so that is problem number 1 in the paper 2, paper 3 section.